So it's an honor for me to introduce the next talk. Leo is one of my heroes. So he has made fundamental and substantial contributions to automated reasoning and SMT solving. He's really revolutionized the way people do e-matching and congruence closure and simplex methods for linear arithmetic and working with real algebraic numbers. In the last few years, I've had the privilege of getting a sense of how he does it. And so I can tell you that when Leo comes to a problem, he first of all learns everything there is to know about the problem. Then he sits and works out a solution that everyone tells him is a great solution, far better than anything out there. After a few weeks, Leo declares it to be worthless, piece of junk, totally and he keeps at it, and he keeps going, and he keeps going until he's really distilled the problem down to its essentials and found the ideal, perfect solution. And then, from then on, that just becomes the standard. And so he's done it over and over again, and automated reasoning has benefited from it. And now the fact that he's interested in interactive theorem proving, we're all benefiting from that as well. So he's going to give a talk about a topic near and dear to my heart. He's going to tell us about metaprogramming with dependent type theory.
Thank you very much. First lesson, you should always get your friends to introduce you. Sometimes I get Shankar to introduce me also. Okay, today I'm going to talk about metaprogramming with dependent type theory. This joint work, almost everybody is here. Gabriel, Sebastian, Jeremy, only Jared is missing. But if you want to learn more about what I'm going to talk today, you can go to these websites. We have the preprints of our paper. But the LinkedIn, we have many more people contributing. Everybody in the first slide is in the LinkedIn, but we also have Mario, Johannes, Flores, Rob, Daniel Selson, and we have former members like Sun Ho and Jacob. But we also we are really grateful for all these people that helped us when we were developing Lean, working on these ideas. When we started Lean, I didn't know anything about dependence type theory, and these people helped me a lot understanding the problems. People keep asking me, why you're building Lean? Well, we started, this is the original, I think it's still valid. The goal for the project is to bridge this gap between interactive and automated theorem provers. There are like two communities. I'm actually from the automated theorem proving community. Some of my colleagues are here, like Konstantin, Larry and Tobias. I think they play in both worlds. They go to CADE, like where all the automated theorem proving people go, and they also go to ITP. But why do we want to bridge this gap? Well, first I can start showing some applications of automated theorem proving in Microsoft. You can roughly divide in two categories, like testing, like you have tools like Sage and PEX. They are for generating test cases and finding security flaws. And you have software verification tools like FStar, VCC, Boogie. And all these tools are based on an automated theorem prover called Z3. The testing tools are actually very successful at Microsoft. Even the product teams use these tools. When Sage, I'm not exaggerating, but Sage sent more than 5 billion constraints to Z3 when it was looking for flaws in Windows 8 and Office and so on. But the software verification tools, there is a problem. I mean, they are usually for easy properties. They are great. You don't need to know anything. If a developer that you don't want to understand things, you don't want to understand what is a proof, they work really well. But as soon as you start to try to prove something complicated, you run into scalability issues, proof stability. It's like you change something that's completely irrelevant, your proofs break, and you have only indirect ways to fix these problems, right? And this was an issue in many verification projects, like Hyper-V, that's a hypervisor, something that runs between the hardware and the operating system. The Ironclad and Iron Fleet, the last two are open source. You can go there and check the source codes of these tools. But this is a recurrent issue. Instability, proof stability and scalability are two big issues. One of the main problems is that these automated reasoning tools like Z3, they are like black boxes. Before I started working on Lean, Grant Passmore and I tried to address this issue, but by allowing users to write tactics on top of SMT solvers, would provide access to some primitives, like you could access the simplex procedure for linear arithmetic. You could write guards that check, oh, if my formula has these properties, I do this, otherwise I do that. You could sequence pre-processing steps. But even with this capability, this is very limited. You don't have access to the internal data structures. You can use these algorithms to build more complicated algorithms. You're basically doing sequential composition, parallel composition. It's very limited what you can do. But it helped a lot to allow people to customize these black boxes in a more convenient way. Then we decided to start Lean. Lean is a new open source improver. It's not so new. We started in the fall of 2013. It's almost 4 years old. We wanted it to be a platform for software verification in formalized mathematics. Right? Both activities are very related. Lean has a very small trusted kernel. Right? We have 2 independent type checkers for Lean, one written in Haskell and one written in Scala. Lean is based on dependency type theory. Before we started the project, we started learning a lot about all these different foundations. Independent type theory, this is a personal view, I think it's really beautiful. One big thing that's the main topic of this talk is the metaprogramming capabilities of Lean. And just to finish the introduction, the first version of Lean was released in 2015 at CADE. But I want to talk about metaprogramming. Right? What's the idea? The main idea is that we want to be able to extend Lean using Lean itself. Right? And we want to give access to all Lean internals, the type inference procedure, the unifier, simplifier, the decision procedures, but just not calling these decision procedures as black boxes, but also being able to access the internal data structures that these decision procedures are building. I'm going to give examples. You can also access the type class resolution, and you can use this infrastructure not just for synthesizing proofs, but for synthesizing programs too. Before I continue with talking about metaprogramming, I want to talk a little bit about this, the logical framework we use in Lean. I used to say that it's based on CIC, but people would complain saying it's not CIC because you don't have a fixed point and a match in your language. I say, okay, now I'm calling CIC minus minus because it has, instead of having fixed point and match, you have recursors. And actually, this is the original paper by Coquin and Pauly Morin. If you go there, they use recursors. They don't have fixed point and match. This was later development. We use inductive families, like as described by Peter. I'm so happy that I met him yesterday. Lean has universe polymorphism and has proofing relevance. And the basic expressions are, you can have sorts like type, you have constants, net is a constant, you can have lambda abstraction, you have function application, function spaces, and non-dependent function spaces. That's just a special case. Very similar to I'm not going to explain this because we had many talks that cover dependency type theory in the previous days. Inductive families. In Lean, you can have indexed data types like natural numbers, trees. You have also indexed families. The inductive family vector is a family of indexed data types because you have an index here, net. You see that it's not uniform, this inductive family. The first constructor builds a vector of size 0, and the second one a vector of size successor of n. As I said, in Lean, we have recursive equations. No, sorry, we have recursors. But recursors are horrible to use, right? I mean, if you have to define your functions using recursors, you're probably not going to be very happy. is in Lean we have a compiler that compiles these recursive equations that's like the ones you write in Haskell into recursors, right? We have several different compilation strategies, like you have structural recursion, well-founded recursion, unbounded recursion. You may say, well, this sounds fishy, but we use unbounded recursion for metaprogramming only. I'll talk more about that later. Here I have two examples. One is by structural recursion, the Fibonacci, and the Ackermann function that's defined by well-founded recursion. How this stuff works? What happens is that the user enters these equations, right? Internally, the equation compiler is going to compile this stuff using structural recursion or well-founded recursion. It's going to automatically generate lemmas showing that the equations you wrote hold, and send all this stuff to the kernel, right? And the kernel is going to type check. It's going to check if the equations are really satisfied by your definition. On the side, we also have the code generator, right? After we generate, right, this definition here, we have a different pipeline where we start that is very similar to the pipeline used in a functional programming language, where you have things like lambda lifting, common subexpression elimination, and so on. And we go into a bytecode that's essentially a stack machine, right? And we have a virtual machine to interpret these bytecodes. We are also working in code generators for C++, and the idea is that you can generate more efficient code. We also have plans. I mean, we want to be able to generate LLVM, and you see that this is useful since you can extend Lean using Lean. Whenever you improve the code generation, you're not just making Lean programs run faster, but you're also making your tactics to run faster. We also have support for mutual recursion. This is a very simple example where I'm computing the number of constants in this very simple inductive data type. You have two functions, one that takes a term into a natural number, and another one that takes a list of terms into a natural number. In Lean, we also have structures. This is just a special kinds of inductive data type. Here I have a point. You have two fields, x and y. The structure command, it does a little bit more than inductive data type. You create the projections like point.x and point.y. If we execute this one here, you get 10, right? If you execute the points, the first one, you get 10. The second one, point y, of the pair 10, 20, you get 20. This notation is horrible. Because it's horrible, we provide better inputs, right? I mean, you can write instance of elements of the type points by writing using curly braces, like in regular programming languages. You can specify the type, in this case, points. But Lean, if the type is known from the context, you don't have to write point dot x is 10, y is 20, right? You can just write x equals 20, x equals 10 and y equals 20. And you can also use projections like in regular programming languages, right? You can use p.x to access the first elements, right? The first fields of the point p. You can also do updates like here, right? So I'm saying I want to build a new point based on p, but I want to update x with 1. You are building here the points 120, right? P is 10, 20, you're updating x with 1. You can also extend structures, right? Basically, I'm creating here a 3D point, and it has an extra field called z, right? This 3D point has x, y, and z. We have type classes in Lean, like Haskell, right? I think now most of the Lean developers are a big fan of Haskell. Here's a type class called sizeOf. where basically you are saying a type is an element of this type class if it provides a function that converts elements of this type into a natural number. And we can provide here several instances. For instance, the highest size of for net is just the identity function. The highest size of for products basically computes the size of a product by computing the size of a pair. A product is just a pair, right? A, B. The size of, we are defining the size of A, comma B by the size of A and size of B plus 1. The point here, this instance is saying what? A product's alpha and beta has a size of if alpha has a size of and beta has a size of, right? And the same, you can do the same thing for the sum type, and you can do for any most of your types. You can start defining these instances. Okay, this is the introduction to Lean. Now let's see a little bit about metaprogramming. I'm going to start with a simple example, right? This find. Find here is taking an expression, a list of expressions, and returning a static expr. What's static? Static, if you're familiar with Haskell, static is a monad. It's used to simulate effectful computations in a pure language. What are the effects here? The effects here are what? You can update your environment, you can access your local context, you can fill the holes in your proof, you're constructing your proof interactively, updating your environment. So these are the effects you have. And basically here, what we're saying is that finds a function with 2 arguments that has an effect called static that allows you to update the environment, to interactively build your proof, and it returns an expression. Okay, you have 2 equations. The first one is saying if E and the empty list, I just fail. This static failed. The second one is saying that if I have E and a list that is headed by age with tail age s, we're going to do the following. First, we're going to infer the type of age using infer type. Then we're going to try to unify E and T. If it unifies, I return age. Otherwise, I keep looking on the tail of the list. What this find is doing is trying to look in the list for elements of the list whose the type unifies with the type with the first argument. That's what it's doing. Now that we know how to do this find, how do? We can write an assumption tactic that we find in many proof assistants. What this assumption tactic is going to do? Here we're using do notation for actions. I'm going to first get in the local context the set of hypotheses. Target is the type that I'm trying to build elements of. And I'm going to say, find in my set of hypotheses something that has the type that unifies with T, right? If I found it, yes, this is my proof. I use age. Otherwise, I say assumption tactic failed. This is a very small example, but this is exactly how it is implemented in Lean, the assumption tactic. Here is a small lemma, basically saying if you have a P and Q are 2 propositions, if you know that it's basically P implies Q, or another way to view is that I have evidence that P holds and I have evidence that Q holds and I want to prove Q, right? You could say, the proof is just H2, but you can use by assumption. It's going to find H2, right? It's going to find an element in your local context whose type unifies with your target, right? That's how the assumption tactic works. Now that we saw this small example, here's how the expressions are reflected. I mean, this is how we are reflecting Lean, the Lean expressions, right? Basically, level here, I'm not going to go into details there, but this is for the universe polymorphism you have in Lean. The most interesting part is expr, right? You have a variable that's a de Bruijn variable. You have local constants that we use to reference hypotheses. You have meta variables that are holes you can view as holes in your terms that have to be filled using statics. You have sorts, constants, applications, lambdas, pi's, and lets expressions. And here's a very small function that's given an expression. Is a recursive function. I'm going to say, if it's an application, I'm going to compute the number of arguments in F and add 1, otherwise I'm going to return 0. It's basically counting the number of nested applications you have, right? And we have this keyword here, meta. When we use the keyword meta in Lean, there are two things. First, you have access to unbounded recursion. You don't need to prove that your programs terminate. They are meta programs. You don't care about these programs. They are used for synthesizing programs that you care or synthesizing proofs you care, right? In Lean is going to do all the bookkeeping. A meta program, a meta definition can use a regular definition, but not vice versa, right? A regular definition cannot use a meta definition. Quotations. You don't want to build terms in this inductive data type. Most of the time, you don't want to use these constructors to build terms because it's quite inconvenient. You want to have a mechanism of quotations. We have two kinds of quotations. The first one is the back quotes parentheses. Basically here, you have a Lean term. What happens here, we are going to, at compilation time, you're going to elaborate this term and create the series of constructor applications that construct this term. And we have the double quote. That's slightly different. The first one is at compilation time, the term is going to be elaborated. The second one is at runtime, is going to be elaborated. Why do we have this distinction? We need this distinction because sometimes elaboration depends on your local context. And your local context depends on the tactics that you executed before you applying this tactic here called refine. For instance, if you are familiar with Cork, you are going to have tactics like intros, simplify, rewrite. You may be changing your hypothesis before you execute, for instance, apply age. The meaning of age depends on what happened before. So you have to elaborate age at runtime at that point. That's why you have two different kinds of quotations. And you can also pattern match with quotations, right? You have this is not, like basically saying if your expression is a not of something, I return this something, or if it's A implies false, I return this something, otherwise it's not a not. And Lean is going to compile this just syntax sugar for this series of constructor applications, right? In this case, it's not so bad to write the constructor applications, but in general, it can be super nasty to write this series of constructor applications manually. Now that we saw how we reflect expressions, let's see how the static monad is represented. The first thing, we have an inductive data type called result that basically has two parameters, state and a value in a type alpha to represent the result. You have two possible outcomes, a success, that you have a value alpha that was produced by your static, a new state, and a new state. And the second constructor is an exception. You can have optionally, you can have a thunk that gives you a description of the error. You can have an optional position saying where your static failed, and you have the state at the time of failure. And we have this interaction monad is a helper definition because static is not the only monad that uses this infrastructure. But basically the interaction monad is anything that takes a state to a result state alpha. And static, our static monad is just interaction monad with this object static state. Static states is reflecting an internal data structure we have inside of Lean, right? Inside of a static state, we have the environments where you have all your definitions, your inductive data types, declarations, and so on. You have your configuration options. You have meta variables explaining what the holes, what it needs to be what is missing, what still needs to be synthesized. Each hole has the context and the type of what needs to be synthesized there. We have a partial assignment. Also, some holes have already been solved. We have the goals that are still open, right? That's when you print in Lean, the goals that are still open is this list here that you are getting. And you have the initial goal also there stored. After we reflected this internal data structure, we also have statics, right? That are exposing functionality that is implemented internally in Lean. Like you have infer type. Giving an expression is going to give you back the type of this expression. Of course, this operation can fail, right? Because this can be a type incorrect expression. You have unification, you give two expressions, and it's going to succeed if the two expressions can be unified. Here, you see the effect going on, right? When you're unifying expressions, some of these meta variables can be assigned. This is one of the effects you have in the static. You have statics for creating a type class instance, for introducing a new hypothesis, for retrieving all pending goals, for setting the set of pending goals. And here you have two statics that's actually used in Lean. They are very simple. With get goals, you can implement them. Like the done static is a static that fails if there are open goals. There still goals to be solved. You just say get goals. Get goals is going to return a list. We immediately try to match with the empty list. If it doesn't match, you fail. Otherwise, you succeed. And target, right, returns the type. What do we do? We get the goals, right? You get the first goal that is G, and you infer the type of this goal. That's the target, what you're trying to, the type of the first goal that you're trying to synthesize, right?
The set goals, can you like modify?
Yes, you can.
That could be unsound. You could change.
No, it's not. Remember, you have a kernel in the end. I mean, if you make a mistake in metaprogramming, the kernel is going to say your proof is invalid. Okay. There's no way to bypass. I mean, you can. The set goals gives you a lot of flexibility because you can implement tactics like focus, at most tactics that temporarily change the set of goals for tactic that's going to be invoked. For instance, you can say execute tactic 1 on this goal only, ignore everything else. Right? You can implement this static in Lean because you have the set goals. Of course, if you make a mistake, you say set goals empty list, and you think you are done. Well, when you send the proof to the kernel is going to reject. Here you have an example to show. I talk about this. We have these automated procedures, like we have decision procedures like the ones in Z3. As I said, they are black boxes. I want to give an example of something we can do because we have access to the internal data structures. This is an artificial example, but I'm trying to make a point. Suppose that you have two functions, f and g. The first one is a binary, this g is unary. You have a predicate p, right? And you have two axioms, f of x equals x, and you have, for all x, p of xx. And you have this goal here that you have three natural numbers, a, b, c, and you have two hypotheses, a equals g of b and a equals b, and you have this goal. One procedure, one kind of automation you have in Lean is a simplifier. You can use like axioms like f of x equals x as a rewriting rule. And you can use the hypothesis as rewriting rules also. You can view a equals g of b as a rewriting rule that goes from a to g of b. If you apply simp in this target, the problem is that you have A can go to G of B, or A can go to B. It's like a non-confluent rewriting system. And you have two possible outcomes. P of F of GB, or P of F GGB, GBB. And if you try to now to apply the axiom P, for all x, P of XX is going to fail. Okay? We can try to avoid this kind of problem by combining two different procedures. One that I'm going to explain in a while is, let's assume for now, I'm going to explain later, that you have a tactic called collect implied equalities. That is a tactic that's going to give you back this data structure that's called CC underscore state. What this data structure it contains there? What you have inside of this data structure is a collection of equivalence classes. Each equivalence class is going to, you can view as a set of terms that are known to be equal. Then after for now, assume that we have this static. Now we can write this function choose, that giving this data structure, CC states, an expression E, we're going to do the following. We are going to traverse the equivalence class of E and look for the smallest one minimal element there. Basically, I'm using a fold for traversing the equivalence class. And we have this best so far, and you have the current expression. If the current expression, the size of the current expression is smaller than the size of the best so far, we return currents as a result, otherwise we keep the best so far. We do these folds looking for a minimal element in the equivalence class. If you're not familiar with Haskell, the $sign notation is just syntax sugar. F $GT is just a way to write F parentheses GT close parentheses. It's just a way to minimize the number of parentheses. The first time I saw it, I thought this was super weird, but actually this is super useful. The Haskell guys, they have a bunch of nice tricks to write clean code. And now we are going to do this rsync. What rsync is going to do? First thing, it collects collects a bunch of implied equalities. Then he tries to do he tries to apply a top-down simplifier, where for each element, each subterm, you're going to give a function here. You're going to, for each subterm T, I'm going to get the root of the equivalence class. I'm going to choose a minimal element in the equivalence class of the root of the equivalence class. Then I'm going to get a proof. I'm going to ask this data structure, give me a proof that T equals T prime. Because you know, this data structure contains not just the fact that everybody in the equivalence class, the semi-equivalence class, it knows they are all equal, but it also knows how to create a proof for them. Right? Then you get this proof, and you return T prime and the proof. The simplifier, this top-down simplifier, expects that a function that gets a term and returns a new term and a proof that T equals T prime. Right? Well, I simplified a little bit how rsync is written, but the main idea is here. If you go, is in the code base. If you go there, you're going to see that is more or less what it's here. I just remove optimizations to make it easier to understand. If you go back to the previous example, you can now solve with rsync, right? Because when you collect this, when you ask lin, the collects implied equality static, you're going to learn this equivalence class that GB, F of GA, F of GA, 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 B, and A. All these terms are equal, right? You figure out that they are all equal using the axiom F of AX, using the hypothesis you have, and congruence, the fact that equalities are congruence. After you do that, rsync is going to be able to simplify the goal to PA or PBB, depending on which B or A is selected as the minimal element. This is an artificial example, but you can use it to solve goals like that, where you have many C operators, you have max and addition, And RSimp can take care of this kind of example easily. Okay, I shown how you can combine two pieces of automation, but I didn't explain how the collects implied equality is implemented, right? To implement that, I'm going to talk about a feature that we use a lot, is that we have the static monads, right? But it's very common when you're writing your own statics that you want to carry additional states, right? You can use something that's in the functional programming community they call a state monad transformer. Suppose that you have a monad M, and you want to carry extra state delta, right? What this monad transformer is a new function from delta to M alpha product delta, right? It's not going to just produce alpha, but it's going to produce the new state delta. Internally in Lean, we have something we call SMT goal. That's the state of the decision procedures implemented in a SMT solver. And you can say that the SMT state is a list of SMT goals, one for each goal in your problem. And now SMT static is just a state monad transformer. You get the static monads we have seen so far, and we add the SMT state. What this gives you is that the capability of, you don't have, many proof of systems are going to have call statics that invoke SMT solvers, like, you can have a static congruence that's going to apply congruence closure. But after the static is done, the state is lost. If you call congruence again, you have to start from scratch. Here, you don't. I mean, when you're inside of the SMT static, you remember the state of these procedures. Everything is incremental. And we implement many procedures that are available in SMT solvers, like e-matching. I'm not going to explain what is e-matching. It's sufficient to know that e-matching is heuristic quantifier instantiation, right? And we can implement a static called eBlast that keeps applying matching while new instances can be generated, and always keep trying to close the goal. You have this eBlast. Now, how the collects implied equality statics works. I'm going to focus on the first goal. Then I'm going to say using SMT, SMT is going to create the initial SMT state. And now, here I'm in the side of SMT static monad. I can update the set of lemmas used for heuristic instantiation using the static. I can call eBlast. Then after I call eBlast, I can try to, if I'm done, I return an empty CC state because I basically solved the goal. Otherwise, I return the state of the congruence closure procedure that contains the set of implied equalities. Basically, this collects implied equalities here is a heuristic procedure that's using congruence closure, e-matching, and there are more things in the SMT state, like you have a decision procedure for associativity, associative and commutative operators, and we are going to keep adding more and more infrastructure there. Okay, this is the example I had to show that procedures are not black boxes in Lean. Now I'm going to show several pieces of automation that were implemented in Lean itself. The first one is a superposition tier improver. It's like 2,200 lines of code. Gabriel implemented this superposition improver. And with it, you can do things like that. You have this example here. You're trying to prove this property about monoids that have an inverse. You can say by super, you provide these two lemmas, and superposition is going to use these two lemmas, and you prove it automatically. But I'm not going to try to explain what a superposition prover. It's sufficient to say that many automated tier provers for first order logic are based on this technology, like Vampire, E, and so on. But we're using the same technique. We're using the state monad transformer. This prover has some states that you have to carry around. In this way, the superposition prover is a monad that is implemented using a state monad transformer. You have the static, the one we've seen so far, plus the superposition prover state, where you have the set of active and passive clauses, newly derived clauses, and so on. Okay, now our next example, to explain the next example, I have this glist. This list is a trick that people use in Haskell to have a list like data type that has a constant time append, right? The idea is that this list is a pair. The first one is a function called apply that takes a list and returns a list, and there is an invariant there saying that apply of L is equals to apply the empty list concatenated with L. And we have functions for converting a glist into a regular list. We have functions here. I'm defining the append operation for the list that is just function composition. Here I'm using this notation as a shorthand for abstract intros rsync. Basically, we are proving that the invariant is satisfied using automation. And we can say now that this append, the list append, is an instance of the hash append type class. This gives us access to the ++ notation, that is the polymorphic notation for append in Lean. And why I'm talking about the list is because Johannes implemented a transfer static. It's like 200 lines of code that allows you to transfer results from one type to another if you can relate them. Basically here, we use to relate lists and the lists, we use lemmas like toList append, saying that the toList of the glist append, if you append two lists and convert to a list, this is equals to convert the first one to a list, convert the second one to a list, and appending, right? You provide these lemmas, you prove these lemmas, and now you can use Johannes transfer function to transfer results from list to the list, right? Here, basically, we are proving that the list is associative, using behind the scenes the fact that list, we already proved that the list append operation is associative. It doesn't need to be a bijection. For instance, Johannes used the transfer static to map results from net to int. You just have to relate the two types. We also have a static that converts Lean to SMT2, right? We have like these intermediate steps. There is this low order logic. This was Jared that implemented this stuff. He found it was funny to call the LOL. But the main point here that all these transformations can be implemented in Lean. He defined this inductive data type to capture the LOL logic. That's a subset of Lean that is closer to what SMT2 accepts, right? So he defines inductive data type. It has a context that's almost like the SMT2 context, where you have type declarations. In SMT2, you actually have sort declarations. You have declarations, and you have a bunch of assertions, right? And then you can write a procedure that reflects Lean expressions in these LOL terms, right? This is for propositions, but it has for arithmetic, for many different kinds of expressions we have in Lean. Another cool example, this one I was surprised at. I mean, Johannes one day said, oh, I'm going to do this in co-inductive predicates. I thought he would not do it, but he actually did it in 1 week. It's 800 lines of code. In Lean, we don't have co-inductive data types, right? But for verifying things like to map projects like CompSert to Lean, right? CompSert has like 12 co-inductive types, but only ones that 11 are like, I don't know, it's around 11. I don't know the exact number, but around 11 are co-inductive predicates. There's only one co-inductive type that's not a predicate. Is the string that we have in Lean already. What was missing to make it convenient to port a project like Concept to Lean was co-inductive predicates. But you don't need to extend the kernel to support co-inductive predicates. You can use the impredicativity of prop to do it, right? In this way, without any kernel extension, you can support co-inductive predicates in Lean, right? What's going to happen behind the scenes is Johannes statics is going to compile this down into the primitives that the kernel accepts, right? In this way, we are not compromising the kernel in any way. The final example, you have just this simple expression language. This is from Adam Shipala's book, this example, right? Where he has an expression, he has an evaluator that converts expressions in natural numbers, he has a few transformations. I'm running a little bit out of time. The message I want to send with this example is that users can write their own search procedure. Here is a very, very tiny, we call it nano crush because Adam Shipala has a tactic called crush. This nano crush, what it's doing is implementing, he uses a text called make relevant lemmas that collects from your environment lemmas that are probably relevant for proving your goal. Then he tries to find automatically some hypotheses for doing induction on. Then he does a search doing some case analysis for looking for proof. This is a very naive procedure, but it's sufficient for proving automatically properties like if you transform this expression with using times k, and we evaluate this is equals k times the evaluation of e. You can do completely automatic the induction, everything is computed automatically. The message here is that you can implement, for some domains, you can come up with a really simple strategy that is very effective, and you can encode it in a few lines of code. Writing tactics is nice, but you also need to debug tactics, right? In this way, and also profile them. We provide a profiler that's based on sampling, right? It's really useful to find performance bottlenecks. We use it very often when writing complicated tactics. And we have also a debugger based on a VM monitor. We actually reflected the virtual machine execution in Lean and allow you to write in Lean a monitor for this, for the execution of the virtual machine. Actually, the command line debugger for Lean is implemented in Lean itself. And as a future work, we want to have IDE support for the debugger. But here's an example of a monitor that I'm just, I'm not going to go over this example because I want to make a demo. I saw Larry is here. Larry, every time I meet him, he asks me, is Lean vaporware? And I want to make a demo. Okay, before the demo concludes saying, users, the main point here is that users can create their own automation and they can extend and customize Lean, right? You can write domain-specific automation that's very reliable for a specific domain. You have not just access to these black boxes that are decision procedures, but you have access to their internal data structures, right? We are exposing all this to users and they can use them to implement their own automation. We call that white box automation. And we want to expose more. I mean, this is, exposing the internal disease is nice for us because users can help. They start writing their own automation, and sometimes they come up with really interesting things. In this way, we want to expose more now. For instance, we want to have structured error messages and trace messages to make all information that Lean produces, to make it first-class citizen in such a way that in Lean you can traverse the information that's produced by Lean. We want to allow the user to write more powerful parser extensions and printers. We want to allow the user to improve the code generator and so on. But before I finish, let's have the small demo. Okay, here I'm inside of Visual Studio Code.
We don't see it.
Oh, you don't see it? Okay, let's see how this stuff works. Okay. Now I don't see it.
Turn on your
I'm old. I mean, I don't know how to do these things. How do you mirror her? Okay.
You need a series bar on the left.
Right, let's see. I think it's this one, right?
Yes, it is.
No.
here.
Yeah.
Mirror display.
Thank you.
Prefer macOS to Windows. That's surprising.
What's happening here? Okay, this is a Visual Studio Code. Here you have a link file. You see that we have type inference. You can hover things, you get the type. Everything's being compiled dynamically. You see you get the red squiggles when you have errors. You can get auto-completion, right? You can see also the proof state. I mean, you see the state as I'm moving. I can see the effects of each static at any point, right? But not now. You can also freeze. I mean, this is useful because now the state is frozen, and I can keep working on my proof. But with the state frozen at a particular point, you can unlock it, and now it's going to be updated automatically. I can simulate here an expensive static, like suppose that I do static slip. Is the number of milliseconds. You're going to see that there is an orange bar saying that this fragment here is still processing the background. The nice thing is that it doesn't block the rest of the file. For instance, if I say foo equals 100, I ask the type of foo. I get the type of foo there. It's a natural number. This guy is still computing in the background. Right, and you see that the orange bar here is saying that this part here is still being processed, but everything else is still available, right? I can, if I remove or I just reduce this leap, you see now it finishes. I mean, you see that 100 is now it just blinked because it's 1 second, but things are being compiled in parallel. Let's see if there's this. Sometimes we show the intermediate states for even this is the rewrite static. We're applying this lemma as a rewriting rule. This one. You can see not just the static, but the intermediate states of the static. You can see what is going on as a. You see it here. It's here changing. You have also things like it's going to. If you hover over statics, you're going to get some information about the syntax the static expects. I didn't cover that, but in this mode here, you have parser extensions for creating this nice syntax for writing statics. You can see also, you can pick on the definition of a static. You can see the implementation here. You can also jump to the definition, not just the static or anything, right? You can see here, let's close this window. Here's the implementation of the revert, right? Say, oh, what's this map? What is this? This is here, the definition, and you can jump. Yeah, it's like integrated development environment for writing your proofs. Yeah, I just I couldn't control myself. My only point is to show that Lean is not vaporware. Thank you very much for your attention.
system?
Yeah, they use the same type system, yes. Yes.
And the evaluation strategy is something like Haskell style?
No, it's called by value.
Or by value?
Yes.
Could you tell us a bit about how you would do the kind of Coq style reflection where you have like you get an unverified certificate and then you have an efficient function
Yes.
in Coq that would evaluate to true if the
Yes.
certificate is good. I mean, could you sort of mimic that here? And if
Well,
so,
the nice thing is that you have access to the lean expression, right? You can write a tactic that converts this expression to your inductive data type, like of polynomials or inductive data type of propositional logic, and you write in lean a decision procedure for this, for propositional or for this inductive data type. Yes, you can do all that, but there is one detail. The lean kernel is minimalistic, right? The Coq kernel has many efficient evaluations, even virtual machines. In lean, we don't have that in the kernel. So you can do all that proof by reflection, but what's going to happen is that, in our experience, this is going to be less efficient than running procedures that generate proofs that are checked by the kernel. Can we add efficient evaluation strategies to the kernel? Yes, we can, but the story, our reference type checkers, you want them to be minimal. Like the Haskell one is like 1,500 lines of code. If you suppose that you do a proof by reflection in lean, you implement a super efficient evaluator. If you want to check this proof with the efficient, with the reference type checker, you're going to have to implement an efficient evaluator there. Otherwise, it will never terminate. But then, I mean, the story of the 1,500 lines is not 1,500 anymore. Yeah, I mean, you have to balance that. I mean,
What would it take to have reflection in the kernel?
reflection here is what we discussed. Reflection in the way he meant.
I mean, what you've shown us, the ability to do metaprogramming,
Yes.
but within the core logic.
In the core, metaprogramming the core. What do you mean by that?
Perhaps we can take it later.
Yeah.
I certainly encourage you to add the parsing and pre-printing. Love to use your superfast kernel, but I, as it were, like to write something in a subset of Agda, for example. Is it just a question of doing it, or are there any fundamental difficulties?
You mean to have something that's like Agda syntax?
Just provide the user with the ability to roll their own syntax.
Yeah, we have. There's even an open
In a
issue.
very flexible way.
Yes,
Obviously
yeah.
You have some syntax extensions,
Yeah.
but they're a bit limited.
Yeah, I mean, like 2 weeks ago, David Christiansen, the Idris developer, visited us. And David is a big fan of rackets. Because rackets you can extend. He's shown how people wrote JavaScript front ends for rackets. He said, oh, we should do that. Yes, we're super excited. Gabriel, Sebastian, we're all excited about this idea of allowing. We have a form of parser extension, but it's not powerful enough to do like Agda syntax. But with this new approach, you can do. We want to support this kind of very powerful parser extensions in the future. Yeah. Yeah, but this is very useful, not just for simulating Agda, but I mean, sometimes you want to create domain-specific languages in Lean, and you want to really nice syntax for this domain-specific language.
It's a way of everybody using your superfast.
Yeah, yeah.
Right?
I find this all very impressive. I'm looking forward to what you will make next. My question is, if I verify a file with theorems, at the end of the file, can I save it like a coq.vo file? Like I've checked this already, I don't need to recheck it when
Yeah, we have object files, not VO files, but
Sure.
.olin files.
Do they contain the lambda terms of the proof?
Yes, yes.
And if you load them, are they rechecked or are they deleted?
Well, there's an option. I mean, you can have when you're in the IDE, you don't want to recheck the terms when you load a module. But you can say trust level 0 in Lean, you're going to recheck everything. Yeah, it's an option. I mean, overnight you can do that. I mean, this is useful if you're paranoid, you think someone changed your object files during the night.
Yes.
Does your metaprogramming language support references, general references?
No, no. But we have, right now we have, it's not references like ML references, but we have now in the static monad, we have something like the Haskell reference. You can say create a piece of state. You get back a reference object, and you can update this reference. But it's not as flexible as ML, right? But you have this capability. Another thing that's is relevant for this question is that in Lean you cannot create cyclic data structures, right? And so you can use reference counting for garbage collection. And one nice thing about reference counting is that if the reference counter is 1, you can do destructive updates. And actually our CodeGen VM does that. If you have an array, what we do sometimes is that you create a reference that's an array. Now if you update the array, if you're the only owner of that array, is going to be a destructive update.
Eve and then Randy.
Oh.
No, okay. So Randy.
You showed us an example of terms with a list of terms as one of the parts of a constructor. What kind of induction principle do you mechanically generate?
Yeah. The kernel actually doesn't support this kind of. This is compiled. What happens is that when you have an inductive data type with a list like expr with a list of expr, what's going to happen? First step, we are going to compile on a mutually inductive data type where you have expr and expr lists. Then we fuse this mutually inductive data type in a single data type using an indexed family. And then we create, automatically creates bijections between expr lists and lists of expr. And this is what's provided to the user. This is a way to make the kernel minimal, make sure the kernel is still minimal. There is only one detail. When you do this kind of transformation, when you define a function, you cannot do it by structural recursion anymore, the way you expect. Your definitions are going to be, by Lean is going to be behind the scenes by well-founded recursion.
I see. And when you define recursive functions, mutually, again, the question comes up.
Yeah. When you have mutually recursion, actually, I can show you. I mean, let's see, this one here. Shankar and I were discussing the other day. Sometimes you don't want, most of the time, you don't want to show how the sausage is made. But you can see if you want. I mean, suppose that you say, oh, I want to see the implementation of num-consts. You're going to see that there is this auxiliary definition main here. You go there. There is another one. You have this mutual num-const lists. Let's do mutual. Oh. Mutual num-const.
There's a space U, right?
Where? Oh, yeah. Thank you. If you go there, you see the well-founded fixed points. There is a bunch of, there's some types there to package. You're packaging everybody using a sum type. If you have it's an array function, you're going to pack with sigmas. Yeah, the sausage is really ugly, but it's hidden from the user.
Doesn't that blow things up badly, or can it blow things up?
Badly.
My comparison is that in Coq, if you define GCD by well-founded recursion, it draws in thousands of lines of library.
Yeah, well.
Because in order to have the well-founded
Yes.
recursion.
Yes. A few comments here. The first thing is that Lean is not just going to generate this ugly sausage here, but it's also going to prove the lemmas for you. When you are reasoning about these functions, you're going to use the lemmas that you automatically generated. The performance issue is only an issue if you want to compute with these functions inside of the kernel, right? The same thing for Coq. If you want to compute the GCD, defined by all-found recursion, in the kernel, it's going to be an issue, but you should probably not do that.
Two more questions, so Andreas.
So how do you handle rollbacks and partial rollbacks on your state, right? Because if a unify succeeds, but then you do other things.
Oh yeah, the static state is internally implements a pure functional object. There are a bunch of optimizations, but the view static state is completely functional, right? The all else is going to do what? You do all else static. You're going to start. We can even see how it's implemented. I mean, if you do check static all else unknown interaction monads. Let's see. Okay. I forgot. People refactor this stuff. Let's see. Like, full T static units. If I do T, what's the name of this guy here? Oh, has. It's a type class, but I know in which file it is. Static. Static dot mean. Oh, else. No, it's interaction.
So else no underscore.
No. It's
It should be an interaction monad.lean and or else in one word.
yes.
Can we have a time off?
Yes. Yeah. Interaction. Okay.
I think we delete.
Yeah.
We don't need to see the proof.
Okay.
Boy, it's purely functional. So one last
I
question.
think I'll take my question offline because people need to have a break.
Okay. So let's thank Leo one more time.
I found it.